Welcome back to The Explainer. Today we're talking about a blueprint for excellence. We're going to break down one of the most recognized standards on the planet for quality management. That's right, ISO 9001.
You ever wonder about this? Think about it. You buy two of the exact same products, and one is just brilliant, works perfectly, and the other is a total letdown. Why does that happen? Well, I'll tell you. It's usually not about luck. It's all about the system or, the lack of a system that's behind that product.
And see, that whole battle, the perfect product versus the dud, that's not something that happens when you, the customer, get it. No, that fight is won or lost way before that, inside the organization itself. It really comes down to a challenge that every single company faces, this huge quest for consistency.
Okay, so this slide just lays it out perfectly, right? On one side, you've got total chaos, you're wasting resources, the results are all over the place, and any success you have is basically a happy accident. But on the other side, you have a system, a real structure, and that brings efficiency, reliable quality, and success that happens by design, not by chance. That, right there, is the core promise of what a good quality management system can do.
So, you might be thinking, what if there was some kind of formula, a globally proven way to get from that chaotic side to the controlled side, a framework that's been tested and trusted by millions of companies all over the world to get that success by design? Well, guess what? There is.
And that's ISO 9000. Now listen to the language here. This is pulled right from the standard's own introduction, and it's so important. It calls it a strategic decision. It's not just a rule book you have to follow. It's a high-level tool, something you choose to do to improve your entire performance and really build a solid foundation for growing in a sustainable way. And this right here is probably the most crucial point to get. ISO 9001 tells you what you need to do, what outcomes to aim for to get quality. But, and this is the key, it doesn't tell you how to do it. That flexibility is it's genius, really. It means a tiny software startup, a giant hospital, a car factory, they can all use the exact same standard to build a system that's perfect for them and their unique situation. Okay, so how does this framework actually work in the real world? Like day to day, what makes it tick? Let's pop the hood and take a look at the engine that really drives the whole thing. The standard itself is super clear about this. It says the core method is something called the PDCA cycle. That's plan, do, check, act. It's this really elegant four-step loop that is, without a doubt, the heart of the whole system. It's what makes sure an organization is always learning, always adapting, and always getting better. All right, so first up, you plan. Think of this as the blueprint stage. You're asking the big questions. What are our goals? What does quality actually mean to our customers? What stuff, resources, do we need to get it done? And here's a big one. What could go wrong? This is where this really important idea of risk-based thinking pops up. It just means looking ahead, trying to spot problems before they happen, and making a plan for them so they don't mess everything up. Okay, so after you've got your plan, what's next? Well, you do. Simple as that. This is the action phase. You take that blueprint and you make it real. You put your people and resources to work, you run the processes you designed, and you actually create the thing you're selling. This is where the rubber meets the road.
And then, after you've done the thing, you check. This part is all about the data. You're monitoring, you're measuring, you're asking, did our process actually work the way we thought it would? Did the final product hit those quality targets we set way back in the plan stage? The whole point here is that you're not guessing anymore. You're collecting cold, hard facts about how you're doing. And finally, you act. Based on everything you learned in that check stage, you start making changes. If something worked great, how do we make that the new standard way of doing things? And if something went wrong, how do we fix it and make sure it never, ever happens again? And that action, well, that feeds right back into a brand new plan. And the whole cycle, the engine of improvement, it just starts all over again. So, okay, the PDCA cycle is the engine, the how. But what's the philosophy? What's the why behind it all? What's the actual soul of this system? Well, for that, we need to look at the 7 quality management principles.
These 7 principles, they're the values that take a bunch of boring procedures and turn them into a real culture. It all kicks off with customer focus. Everything has to be about them. Then you need strong leadership to set the direction. You've got to have engagement of people, getting everyone on board. It's all about using a smart process approach and making decisions based on evidence, not just gut feelings. And maybe most importantly, it's about making improvement a constant habit, not just a project you do once.
And that is the real goal here.
Look, without these principles, all those processes and procedures, they're just bureaucracy, a tangled mess. But when you build on these principles, you create a real culture of quality. It becomes part of your company's DNA. So, after all that, the system, the cycle, the principles, let's get to the bottom line. Why do all this work? Why build this whole blueprint for quality? What's the actual payoff?
Well, the benefits are incredibly clear, and they're powerful. First, you get consistency. You can deliver what you promise every single time. Second, satisfaction. You find real ways to make your customers happier. Third, risk management. You have a system that helps you see problems coming and deal with them. And fourth, credibility. You can show the whole world that you meet a globally recognized standard for quality. That's huge.
And at the end of the day, this isn't really about passing some audit or getting a fancy certificate to hang on the wall. It's so much more than that. It's about building an organization that's strong, that's resilient. It's a genuine strategic investment in a foundation for success that's going to last for the long haul. So I'll leave you with this one last question. Think about your own organization. Is it operating by design with a real system that's built for quality? Or is it still just leaving success up to chance?
Welcome to The Explainer. Today, we're going to demystify something called IATF 16949. Now, that might sound like a bunch of letters and numbers, but it's actually the essential quality standard that keeps the entire global automotive industry running smoothly. Bottom line, if you make parts for cars, this is your playbook.
Okay, so here's how we're going to break it all down. First, we'll cover what IATF 16949 actually is. Then we'll look at its foundation, which is the famous ISO 9001. After that, we'll get into the nitty-gritty, the automotive core tools. We'll touch on some other big highlights of the standard, and finally, we'll zoom out to see how it all comes together as a framework for quality.
All right, let's jump right in. What exactly is IATF 16949? To really get why it's so important, we have to go back and look at the problem it was designed to solve for the massive, complex world of automotive manufacturing.
So it all goes back to a group called the International Automotive Task Force. You'll hear them called the IATF. Now, before they came along, it was kind of the Wild West. You had all these different quality standards in different countries. It was a mess. So the IATF's whole mission was to create one single unified global standard that everyone in the supply chain could follow.
And IATF 16949 is the result of all that work. You can think of it as the one global rulebook for quality management for anyone, and I mean anyone, who makes parts or provides services for the auto industry. It basically created a common language for quality that works everywhere in the world. Now, this quote really gets to the soul of the standard. It's not about having inspectors at the end of the line catching mistakes. No, the entire philosophy is about being proactive. It's about building a system that prevents defects from ever happening, that reduces tiny variations, and that cuts out waste way upstream in the process. Okay, so here's a really key point. IATF 16949 doesn't just exist in its own little bubble. It's actually built on top of a much broader, more universal quality standard that's used in pretty much every industry you can think of. Right, and that standard is ISO 9001. The best way to think about it is this. ISO 9001 is the solid foundation for any good quality management system. It's the universal starting point. Then, IATF 16949 comes in as a supplement, like a set of high-performance blueprints, adding all the specific and frankly much tougher requirements that you absolutely need for the car business.
And one of the biggest ideas it shares with ISO 9001 is something called the process approach. It sounds technical, but it's simple. It just means you stop looking at tasks as isolated little islands. Instead, you see your entire company as a system of interconnected processes. The end of one process is the beginning of the next, and you have to manage how they all link up.
So what drives this whole system? What keeps it moving forward and getting better? Well, it's this cycle. Plan, Do, Check, Act, or PDCA. It's the engine for continuous improvement. You come up with a plan for a change, you actually do it, you check the results to see what happened, and then you act on that information, either by making the change permanent or by tweaking your plan and trying again. It's a constant loop.
All right, now we're getting to the really practical part. This is the heart of it. If you think of the IATF standard as telling you what you need to achieve, then these things, the automotive core tools, they tell you exactly how to do it. And yeah, these are absolutely mandatory.
So there are 5 of these core tools, and what's so brilliant about them is that they're not separate things. They're designed to work together, feeding into each other. They create this complete, closed-loop system that manages quality all the way from the first glimmer of an idea to mass production. So let's do a quick rundown of each one. First up, you've got APQP, which stands for Advanced Product Quality Planning. Honestly, just think of this as the master plan. It's the structured roadmap that takes a product from a simple concept all the way through to launch, making sure that quality is planned and built in at every step of the journey, not just inspected at the end.
Okay, next on the list is PPAP, the Production Part Approval Process. The best way to think of this is like the final exam before you're allowed to start mass production. It's where you gather up all the evidence, all the measurements, all the tests, and present it to the customer to prove, hey, we understand exactly what you need, and our process is 100% ready to deliver.
Then there's FMEA, or Failure Mode and Effects Analysis. This one is like your crystal ball. It's a tool for looking into the future, a future where things might go wrong. You get your team together and you systematically brainstorm everything that could possibly fail in your product design or your manufacturing process. And then, and this is the key part, you take action to prevent those failures before they have a chance to happen.
After that, we've got SPC, Statistical Process Control. Think of this as the heartbeat monitor for your manufacturing line. You're using statistics and charts to watch your processes in real time. It helps you understand the difference between the normal, everyday little variations and a special problem that's popped up and needs your immediate attention.
And finally, we have MSA, or Measurement Systems Analysis. This one is so critical because all that great data you're collecting for SPC, well, it's totally useless if your measuring tools are off. MSA is the tool you use to analyze your measurement system itself, the gauges, the methods, even the people doing the measuring, to make sure the data you're basing your decisions on is actually accurate.
But here's the thing, IATF 1699 goes so much deeper than just the parts being made on the production line. It's really about the entire business. Let's take a look at just a few other requirements that show you just how wide its scope really is.
I mean, check this out. The standard has huge requirements for product safety, making sure you have documented processes to keep customers safe. It forces you to do deep risk analysis, learning from past issues like product recalls or customer complaints. It even requires you to have contingency plans. What happens if a key machine breaks down, or a supplier can't deliver, or you get hit with a cyber attack? You have to have a plan. And it even covers corporate responsibility, things like anti-bribery policies and codes of conduct.
Okay, so we've covered a lot of ground. What's the big takeaway here? When you put it all together, what does IATF 16949 really represent?
And this really is the most important part. IATF 161949 is not just about passing an audit so you can hang a certificate on the wall. That's just the beginning. The real goal, the true spirit of the standard, is to use it as a framework to build a powerful culture of quality, a culture of managing risk, and a culture of always looking for ways to get better.
So that leaves us with one final question for you to think about. Just take an honest look at your own work, your own processes. It doesn't even matter if you're in the auto industry. Is your system set up to proactively prevent problems from ever happening, or do you find yourself mostly reacting to them after the fact? Because making that fundamental shift from reactive to preventive, well, that is what IATF 1699 is all about.
All right, welcome. Today, we are diving deep into what are known as the 6 core quality tools. Now, this is a system that was born in the super high-stakes world of automotive manufacturing, and it completely changed the game. And it did it by focusing on one simple but incredibly powerful idea. Stop fixing problems and start preventing them from ever happening in the first place.
So, here's our roadmap. We're going to start with the core philosophy, the big idea that drives this whole thing. Then, we'll journey through the process, starting with the planning phase, moving to the execution on the factory floor, and then all the way to the final approval. It's a really logical flow.
Okay, first things first, let's talk about that core philosophy. Before we even touch on a single tool, you've got to understand the fundamental mindset shift that makes this entire system work. It's a big one.
You see, for the longest time, quality was all about detection. It was about finding mistakes after they were already made, inspecting them out, fixing them, scrapping them. But this system, it's a whole new ballgame. It's all about prevention. It's a total shift from being a really good firefighter to being a brilliant architect who designs a building that's fireproof from the start.
Okay, so with that prevention mindset locked in, let's get to the planning phase. This is where we look at 2 absolutely key tools that are all about creating a rock-solid blueprint for quality, long before a single part ever gets made.
The first tool is called APQP, which stands for Advanced Product Quality Planning.
The easiest way to think about this is as the master project plan. It's this super structured roadmap that makes sure every single step of the process is thought about, planned for, and done on time.
And to see why this is so important, just think about a kitchen renovation. Without a plan like APQP, it's chaos, right? The cabinet guy starts building before the final dimensions are locked in, then the homeowner picks a new fridge that doesn't fit, now you're moving walls, things get delayed, costs go through the roof, it's a nightmare. But with APQP, you create that detailed plan up front, the layout's confirmed, the appliances are chosen, everybody knows their job, materials show up when they're supposed to, and the whole project gets done on time, on budget, and you've got a very happy customer.
Okay, so APQP gives us the master plan, but even the best plans can go sideways. So how do you anticipate what could possibly go wrong with that plan? Well, that's where our second tool comes in, FMEA, or Failure Mode and Effect Analysis.
The airbag analogy just nails this concept. So without FMEA, a team might use a new, cheaper sensor to save some money, but they never really consider what might happen if it gets really cold. The car launches, winter hits, and suddenly airbags aren't deploying. You've got a massive, dangerous, and incredibly expensive recall on your hands. But with FMEA, the team sits down from day one and just asks, what if? What if the sensor fails in the cold? What if the material tears? They identify all those risks and design solutions for them from the very beginning, so the airbag is safe no matter what.
Now that our plan is solid and we've thought about the risks, we shift from planning to actually doing. This is the execution phase, and here we use 3 tools to make sure we get quality and, just as important, consistency on the actual production line. The first tool we need here is the control plan, and you can just think of this as the official, non-negotiable recipe. It's a document that spells out exactly how to control the process to make sure the final product is perfect and consistent every single time.
This is exactly why a coffee from a huge global chain tastes identical no matter where you are in the world. They have a bulletproof control plan. It doesn't matter if it's Ram making your coffee on Monday or Sham on Tuesday, they use the exact same amount of beans, the exact same grind, the same water temperature. The control plan takes all the guesswork out and just guarantees consistency. But that leads to a really critical question, doesn't it? A recipe is fantastic, but it's only as good as your measuring tools. I mean, what if your thermometer is off by a few degrees? What if your scale is broken? How can you trust anything at that point?
And that is where MSA, Measurement System Analysis, comes into play. It's basically a scientific way to put your entire measurement system under the microscope. Not just the tool, but the people using it, the environment, the whole shebang, to verify that you can actually trust the numbers it's giving you.
Imagine you're making engine pistons. If the caliper you're using to measure them is faulty, you're in deep trouble. You might be throwing away perfectly good pistons, and even worse, you might be approving bad ones that'll cause an engine to fail. It's a disaster. But with MSA, you first verify that caliper against a perfect standard. You prove the system is reliable, so you know without a doubt that the decisions you're making are based on data you can actually trust.
Okay, so let's recap. We've got our recipe, the control plan. We trust our measuring tools thanks to MSA. Now we can start keeping an eye on the health of our process in real time. And we do this using SPC, or Statistical Process Control. The cookie analogy here is just perfect. Imagine an industrial oven, and someone accidentally leaves the door just a tiny bit ajar. Without SPC, you might not notice until you've burned thousands and thousands of cookies. But with SPC, the baker's measuring a few cookies every 15 minutes and plotting the results on a chart. The second a measurement starts to drift outside the normal limits, it's like a big alarm bell goes off. They can check it out, find the open door, and fix the problem, saving the rest of the batch. It's an incredible early warning system.
All right, we are on the home stretch. We've planned everything, we've analyzed the risks, we've controlled the process. Now it is time for the final proof. We need to prove that this whole system we've built actually works and is ready for mass production.
This is where PPAP, the production part approval process, comes in. And you can literally think of it as the final exam for your entire quality system. It's that moment where you, as a supplier, formally go to your customer with all the documented evidence and prove that you can consistently produce parts that meet every single specification.
And here's why this is so huge. PPAP prevents you from making incredibly expensive assumptions. Without it, a supplier might go ahead and make 200,000 smartphone screens, ship them off with confidence, only to have the whole lot rejected. But with PPAP, you produce a small trial run first. You submit all the evidence, the risk analysis, the control plan, the measurement data,
and you get that formal approval from the customer. Then, and only then, do you hit the big green button for mass production.
And this is how it all just comes together in this beautiful, logical flow. You see, these aren't 6 random tools you just pull out of a toolbox. They build on each other. You start with the plan, your APQP. You use FMEA to analyze the risks, which then feeds into your control plan, the recipe. You use MSA to make sure you can trust your data. Then you monitor the process with SPC. And finally, you prove it all works with the PPAP final exam.
So, what's the big takeaway here? This system isn't really about the individual tools. It's about building a culture. It's a proactive, data-driven way of thinking. It's all about that commitment to preventing problems, to planning ahead, to guaranteeing consistency, and to making smart decisions based on data you know you can trust.
And to wrap this all up, I'll just leave you with this question to chew on. This prevention mindset completely revolutionized manufacturing. So where else in your work, or heck, even in your day-to-day life, could applying this idea of preventing problems, instead of just getting really good at fixing them, be a total game changer?
So let's talk about APQP. You've probably heard that acronym thrown around in manufacturing. It stands for Advanced Product Quality Planning. And honestly, it's the secret sauce the big players use to make sure new products launch without a single hitch. We're going to break down exactly how it all works. You know that feeling, right? You get a brand new phone, maybe a new car, and then, bam, a recall. It's so frustrating. And you have to wonder, how does that even happen? Well, most of the time, it's because a tiny mistake was made way, way back in the planning stages. And that is exactly the problem APQP is here to solve. Think about launching a new product, like trying to walk through a minefield. Seriously, if you don't have a map, you're going to have a bad time. So let's take a closer look at some of those mines, the common pitfalls that can totally wreck a project and lead to those recalls we were just talking about. And what's crazy is how these problems just snowball. Like maybe the product doesn't do what customers actually want because nobody was clear on the goals to begin with. Or the assembly line is all over the place, so you get good parts, then bad parts. Or, and this is a big one, you just can't make the product fast enough. We're talking about massive, multi-million-dollar failures here. Okay, so how do you get through that minefield safely? You need a map, a proven strategy. And that strategy is APQP, Advanced Product Quality Planning. Its whole deal is about getting ahead of problems before they ever happen. If there's one word you need to remember from all this, it's proactively. That's the heart of APQP. It forces everyone to stop and think, okay, what could go wrong here? Both with the product design and with how we're going to build it. The whole point is to build quality in from day one. It's not just about making a cool product. It's about making a system that can build that cool product perfectly every single time. And here's the thing. APQP doesn't work alone. It's kind of like the captain of a team. It's one of 5 quality core tools that came out of the auto industry. You've got other tools on the team like FMEA, that's for spotting risks, and SPC, which is for keeping an eye on production. APQP is the playbook, the master framework that tells all these other tools when and how to get in the game. All right, so APQP is basically a journey, and it's got 5 main stops along the way. We're going to walk through this whole roadmap together, right from that first light bulb moment all the way to when the product is rolling off the line. So here's the big picture. You can see how it all just makes sense, right? First, you plan everything out. Then you design the actual product. Then you figure out how to build it. After that, you test it to make sure it all works. And finally, you hit go on production and keep making it better. See? Each step just flows right into the next. Okay, phase 1. This is where it all begins. Think of it like the foundation of a house. If you mess this part up, well, the whole project's going to be wobbly. The main goal here is to really listen to what the customer wants, the voice of the customer, and turn that into a solid, actionable plan. And this is how that translation happens. You take all your inputs, like customer feedback, market research, all that stuff, and you turn it into concrete outputs. What are our design goals? What are our quality targets? We even put together a first draft of the bill of materials, which is basically the shopping list for the product. This phase sets the North Star for the entire project. All right, on to phase 2. We've got our plan, so now it's time to focus on the product. This is where the engineers get to work, taking all those goals we just set and turning them into actual blueprints and specs. So the main thing that comes out of this phase is the product blueprint. And yeah, that means detailed drawings, but it also means something called a design FMEA. That's just a fancy way of saying we're doing a risk assessment on the design itself. We're asking, what are all the ways this thing could break? And fixing those problems now on paper before we spent a dime on tooling. We also map out how we're going to check the quality on the very first prototypes. Okay, big shift here for phase 3. We've designed the what. Now we have to design the how. We're moving from designing the product to designing the process that's going to build it. The big question is, how are we going to make thousands of these things, all identical, all perfect? And the outputs here are basically the blueprints for the factory itself. We're talking process flow charts that map out every single step. We're creating the actual layout of the assembly line, and we're putting together a pre-launch control plan, which is our game plan for quality control during those first few production runs. Like we said, we're building the system that builds the product. Okay, so we've got a product design, we've got a process design. Now comes phase 4, the moment of truth. This is where we find out if it all actually works together in the real world. You could call this the prove it phase. And how do we prove it? We do what's called a significant production run. We fire up the real assembly line with the real tools and we make a real batch of the product. We check to make sure our measurement tools are accurate. We see if the process is stable, and this all leads up to getting a PPAP. That's the production part approval process. Once that's approved, we've officially got the green light for full-scale production. All right, the product is rolling off the line. Time to chick back and relax, right? Nope, not even close. Phase 5 is all about what happens next. It's a continuous cycle of making the product, getting feedback, and making things better. The job is never really done. So in this final phase, we're always looking for ways to improve. We use tools like SPC, Statistical Process Control, which is just using data to watch the process in real time and spot any wobbles. If a problem does pop up, we have structured ways to solve it. And maybe most importantly, we write down everything we learned, the lessons learned, so that the next time we do this, we're even smarter. Now look, APQP is an amazing framework, but it's not a magic wand. For it to actually work, a few things have to be in place. Without them, even the most perfect plan can just fall apart. It really comes down to 3 things. First, you need management to be all in. They've got to provide the money, the people, the support. Second, you have to get everyone talking to each other. No more silos. Engineering, manufacturing, quality, they all have to be on the same team. And third, you need somebody keeping the whole train on the tracks with really solid project management. Okay, we've mentioned this acronym a couple of times, PPAP. Let's really nail down what it is, because it's pretty much the grand finale of the whole APQP process. It's the final exam. I love this analogy because it makes it so clear. Think about it. APQP is the blueprint, the plan, the entire construction process of building a giant skyscraper. The PPAP? That's the certificate of occupancy you get at the end. It's the official document that proves you followed the blueprint and that the building is safe and ready to go. And when we say proof, we mean proof. It's not just a thumbs up. In the auto industry, a full PPAP submission is a package with 18 different items. We're talking everything from the original drawings to lab reports on the materials, all the way to the final sign-off form that gives the supplier the official okay to start shipping parts. So let's wrap this up with one last question for you to think about. When it comes to your process, is it built on a solid plan or is it built on a prayer? Are you following a blueprint like APQP, or are you just winging it and hoping for the best? Because in today's world, hope is not a strategy. A plan is. All right, welcome. Today we're going to dive into a topic you've probably never even thought about, but it's the reason the car in your driveway actually works. It's the hidden system that brings order to the absolute chaos of global manufacturing. It's called PPAP. Let's get into it. I mean, really, stop and think about this for a second. A single car has something like 30,000 parts. And those parts come from all over the world, from thousands of different suppliers. So how do you make sure the little screw made in Germany fits perfectly with the plastic bracket made in Mexico? If you get that wrong, it's not just a customer complaint. It's a potential disaster. And that right there is the core of the problem. How do you guarantee consistent quality when your supply chain literally wraps around the planet? It's a massive, massive challenge for any big company. You know, before we had the system we're talking about today, things were, well, kind of messy. The approach was all over the place. A quality check in Europe could be totally different from one in Asia, and that just created a ton of confusion, wasted time, and worst of all, a whole lot of risk hiding just beneath the surface.
So obviously, that kind of inconsistency just wasn't going to work long term. The industry had to evolve. It had to move away from that loosey-goosey collection of regional process audits, or PA, and create a single, tough global standard, the Production Part Approval Process, or PPAP. And this is where it gets so interesting. Just look at how directly PPAP tackles the problems of the old system. Instead of every region doing its own thing, boom, one global method for everyone. Instead of subjective questions that could mean anything, nope, simple, clear yes or no questions, no gray area. And where you couldn't really see the risk before, PPAP builds it right in with a scoring system. They even streamlined the whole thing, cutting out almost 100 questions. Think what's the time and money that saved. It's just smarter. Okay, so we've set the stage for why this whole thing needed to happen. But what exactly is PPAP? What's at the heart of this standard that changed everything? Now, if you take away just one thing today, let it be this. PPAP isn't about checking a single finished part. It's about approving the entire process that makes the part. The whole point is to prove with cold, hard data that a supplier can churn out a perfect part, not just once, but reliably over and over and over again. And it's important to note that PPAP doesn't just exist in a vacuum. It's actually a critical piece of a much bigger strategy called Advanced Quality Planning, or AQP. The whole idea here is that you don't wait until the end to check for quality. No, you design it in from the very, very beginning. It's proactive, not reactive. So, when do you need to do a PPAP? Well, it's not a one-and-done deal. It's all about managing change. Anytime you have a new part, you gotta do a PPAP. Anytime you change the supplier's process in any significant way, you need a PPAP. If the tools for that part haven't been used for over a year, yep, you guessed it, PPAP. It's a living process that ensures quality stays high for the entire life of a part. All right, so we get what it is and when it's needed, but what does one of these audits actually look like? What's inside? Come on, let's pop the hood. The entire process really boils down to this one massive, comprehensive file. And I don't want you to think of it as just paperwork. It's more like the prosecution's evidence in a court case. It's the complete, undeniable proof that a supplier is ready for mass production. And man, this list really gives you a sense of just how deep this thing goes. A full PPAP file has 18 sections. We're talking everything from the original blueprints to these super intense failure analyses. That's the FMEA, all the way to control plans and statistical data. It all builds up to the final sign-off, the Part Submission Warrant, or PSW. That's the golden ticket. Okay, so you've got this mountain of information, right? It's a lot to take in. So how does an engineer look at all this data and boil it down to a simple, clear decision about risk? Well, the answer is actually brilliant in its simplicity. They use a system that all of us learned as kids, a traffic light. It works exactly like you'd think. Every single requirement in that audit gets a color. Green means you're good to go, the requirement is met. Yellow is basically a proceed with caution sign. It's not totally satisfactory, but the risk is low and probably manageable. But red, that is a hard stop. It means you have a high-risk problem that has to be fixed, period. No exceptions. But it gets even more sophisticated than just colors. PPAP uses a special metric called the Risk Priority Number, or RPN. The best way to think about it is like a credit score, but for risk. It's a number calculated from 3 key things: how severe a failure would be, how often it's likely to occur, and how easily you can detect it. This gives engineers one single number to help them focus their energy on the biggest problems first. And that RPN score isn't just pulled out of thin air. It's informed by some really critical factors. Things like how mature is the design? Is it brand new or tried and true? How capable is the supplier's actual factory? And what's the real-world impact of this specific part on the finished car? This 360-degree view is what makes the whole risk assessment so robust. So when you put all these different pieces together, the global standard, the deep dive audit, the simple risk assessment, you realize it's all in service of one single, incredibly important mission. And really, it all comes down to this. The goal is to create processes that are so good, so competent, that they guarantee perfect parts in the right quantity, delivered on time every time. This is what makes PPAP more than just a boring procedure. It's a core philosophy for anyone who wants to be truly world-class. So the next time you get in your car and turn the key without even thinking about it, just take a second. Remember that there's this massive, invisible, incredibly rigorous system working in the background to make sure every single one of those 30,000 parts is as close to perfect as humanly possible. That's the real power of PPAP. It's the hidden engine of reliability in our modern world. It kind of makes you wonder, right? What's one thing you use every day that you trust completely without ever thinking about how it's made?
You know that feeling when you're looking at a report, staring at the data, and you just know deep down that something is off? We make massive decisions based on numbers every single day. But what if the way we're getting those numbers is actually the problem? Well, today we're going to dive into exactly that with something called measurement system analysis, or MSA, to figure out if our data is actually telling us the truth.
But hey, before we get into all the technical stuff, let's just start with a really simple question. When it comes to a basic task, like just counting something, can you always trust yourself to get it right? Let's put it to the test.
Okay, let's play a quick game. You're about to see a paragraph on the screen. Your only job, your one single mission, is to count every single letter F you see. That's it. You've got 30 seconds on the clock. You ready? Go.
All right, time is up. Got your number? Go ahead and lock it in.
So how'd you do? The actual correct answer is 48. Now, if you got something different, you are in very, very good company. Seriously, when I do this with a live audience, the answers are all over the place. And this is a perfect demonstration of the key idea here. The second a human being gets involved in any measurement, you introduce variation. It has nothing to do with intelligence, it's just how our brains are wired.
That little counting game is the perfect jumping off point for what we're going to cover. First, we'll see how this exact kind of variation creates huge problems in the real world. Then, we'll need to define accuracy and precision to even know what a good measurement looks like. From there, we'll dig into the two main culprits of measurement error, see how to pull them apart, and finally, answer the big one. Can we actually trust our data? All right, section 1. You might think that counting game was kind of trivial, but it's actually a perfect small-scale model of what happens every single day in the real world. Except out there, the stakes are a lot higher than just missing a few letters on a screen.
Just take a look at these real examples. You've got an HR department that gets totally different employee satisfaction scores than an outside firm does. Why? Well, maybe people answer the questions differently depending on who's asking. Or here's a classic, a factory where the day shift and the night shift are in a constant war, always readjusting the glue rollers, each one blaming the other. Get this, it turned out 35% of their variation was just from how people were measuring. These aren't process issues, they're measurement issues pretending to be process issues.
So, to fix a measurement problem, we have to start with the right language to even describe it. And that brings us to two of the most critical concepts in this whole field, accuracy and precision. They sound kind of similar, but trust me, they tell us two completely different things about our system.
The best way to think about this is a dartboard. Accuracy is all about your average. If you throw 10 darts and they're all over the board, but their average position is the dead center bullseye, congratulations, you're accurate. Precision, though, that's about consistency. Are all your darts packed into a tight little group? Now, what's really important to get is that you can be incredibly precise without being accurate at all. Just imagine all your darts landing in a tiny cluster the size of a quarter, but way up in the top left corner of the board. This really gives us 4 possible outcomes. Scenario A is just a disaster. Your shots are everywhere, you're neither accurate nor precise. B is when you're precise but not accurate. That tight cluster we just talked about, but nowhere near the target. C is, accurate on average, but your shots are all over the place. The goal, the gold standard we're all shooting for, is D. You are both accurate and precise. A tight cluster right on the bullseye.
Okay, now we can get to the absolute heart of what's called a Gage R&R study. The R&R stand for repeatability and reproducibility. And these two ideas are how we diagnose our problems with precision and figure out the exact source of all that inconsistency.
So let's start with repeatability. The easiest way to think about this is equipment variation. It's asking a really simple question.
If the same person measures the same part with the same tool over and over again, do they get the same answer every time? If I measure a sticky note 3 times in a row and get 3 slightly different numbers, that's a repeatability problem. The issue isn't me, it's probably the tool.
Reproducibility, on the other hand, is all about the people. This is a Praiser variation. So if I measure the sticky note with my ruler, and then you come along and measure the exact same sticky note with the exact same ruler, do we get the same number? If we don't, that's a reproducibility problem. Maybe I read the ruler from a different angle, or you press down harder. This is exactly what happened in our Count the F's game.
Okay, so we've got our concepts down. Now let's see how they all snap together in a real study. The whole purpose of a Gage R&R is to take all the variation we're seeing in our data and sort it into different buckets so we can finally understand what's really going on. So when we measure a bunch of stuff, the total variation we see really only comes from 3 places. First, there's the actual part variation. And guess what? This is the good stuff. We want to see differences between our parts. That's the whole reason we're measuring them. Then you have the 2 sources of error we just talked about. Repeatability, which is the noise coming from our equipment, and reproducibility, the noise coming from our people. And boom, here it is. This table right here is the money shot of a Gage R&R study. It tells the whole story. Just look at that part-to-part line. It's over 92% of the variation. That is fantastic news. It means our system is actually detecting the real differences between the parts. Now look at the total Gage R&R. That's our measurement error, our noise, and it's less than 8%. This is the sign of a really healthy system. But check this out. A chart like this can show us exactly where that 4-point-something% of reproducibility error is coming from. It tells a story that the numbers alone just can't. You can see it clear as day. Operator A is always measuring high, operator C is always measuring low, and B is kind of in the middle. They are not getting the same results. We don't know who's right just yet, but we know for a fact they have different methods, and our next step would be to figure out why. So we have the numbers, we have the charts, but what's the bottom line? How do we make that final call and decide if we can actually trust our measurement system to make big decisions? Well, this all comes down to a really cool concept, signal versus noise. I'm about to tell you something you will almost never hear in the world of quality control. Ready? In this chart, out of control is a good thing. Yeah, I know, it sounds completely backward. But in this one specific part of a Gage R&R study, it's exactly what you are hoping to see. And here's why that crazy statement is true. It's all about signal versus noise. An out-of-control X-bar chart is proof. It's proof that your measurement system is sensitive enough to actually see the differences between the parts. The variation between the parts, that's your signal. The variation from your measurement system, that's the noise. You want that signal to be so loud that it completely drowns out the noise and breaks right through the control limits. So what's the final verdict? What's the rule? Well, the general rule of thumb is this. Your total measurement system error, that total Gage R&R number, should be less than 10% of the total variation. If you can get your noise under that 10% threshold, your system is considered excellent. And if we look back at our example, that's exactly what we found. That big, beautiful 92% slice of the pie was the real deal. That was the signal coming from the parts. And that tiny little slice, less than 8%, that was just measurement noise. This is what gives us the confidence to know that when our data moves, it's because something real has changed, not because we're just chasing ghosts in the machine. And that right there is the power of a Gage R&R. It helps you stop chasing ghosts and start focusing on what's real, which really just leaves one last question for you to think about. From the surveys you run, to the products you make, to the experiments you do, where's the hidden measurement variation in your world? Think about this for a second. Imagine spending all this time, all this money, building thousands of products, only to find out at the very end that a huge chunk of them are totally useless. It's this incredibly costly problem of finding mistakes way after they've already happened. Today, we're going to dive into a really powerful idea that's designed to stop that madness: statistical process control, or SPC. And it's all about stopping errors before they even have a chance to start. So how do you do that? Well, it all starts by flipping the script. Instead of asking, hey, how do we find the bad parts? We ask a much smarter question. The one you see right here. How do we make sure our process only creates good parts? You see, that fundamental shift in thinking, that is the entire reason SPC exists. And this slide just lays out the difference perfectly. It's night and day. On the left, you've got the old way, finding faults.
It's completely reactive, right? You've already spent the time, the money, the materials, only to end up with a pile of scrap. But on the right, that's the new way, preventing faults. This is all about controlling the process itself, making it so stable and predictable that you just know the output is going to be good from the get-go.
And this quote right here, man, it just nails the change in mindset. Finding faults, like it says, is about tolerating error. You're basically building waste right into your budget. But prevention, that's about designing a system to avoid error altogether. The whole goal is to make it right the first time, which saves a ton of resources, builds trust with your customers, and, ultimately wins.
So, how do we get there? How do we achieve this? Well, it all starts with understanding one thing: the source of pretty much every single problem in any process, variation. Because if we can understand why things vary, we can learn how to control it.
So what exactly is variation? It's actually super simple. It's just the fact that no two things are ever exactly the same. I don't care if you're baking cookies or manufacturing microchips, there will always be tiny little differences in the output. It's just a fundamental law of how the world works.
Okay, and this is where it gets really interesting. Variation breaks down into two critical types. On the left, you've got natural causes. Think of this as the built-in, predictable background noise of a stable process. A great analogy is your body temperature. It goes up and down a little bit all day, and that's totally normal. But on the right, you have special causes. These are the game changers. These are the unpredictable events that mess things up. This is like getting a fever. It's a massive, clear signal that something unusual is happening, and you better pay attention.
So here's the million-dollar question. How do we separate that normal, everyday background noise from those fever spikes that signal a real problem? We need a tool, something to make all this variation visible. And that tool is the control chart. And its heart is just a simple graph that plots your process data over time. Now, that over time part is absolutely key. It turns a boring list of numbers into a dynamic story. It's like a movie of your process, letting you see patterns, shifts, and outliers as they happen in real time. It's the first step to really understanding what your process is up to.
And you know what? Building one is pretty straightforward. It's a simple 3-step process, just like you see here. First, step 1, you just plot your data points over time. Easy enough. Second, you calculate the average of all those points, and that gives you your center line. And third, using some basic stats, you figure out your upper and lower control limits. These limits define the expected range of all that normal, natural variation we talked about.
And voila, this is the result, a finished control chart. You've got your data, the center line, an upper control limit, and a lower one. Now, it's so important to get this. That space between the limits, it isn't based on what you wish would happen or some target you pulled out of thin air. No, that's what we call the voice of the process. It's your process, based on real data, literally telling you what it's actually capable of doing, day in and day out, background noise and all.
Okay, now for the really powerful part. Once you have the chart, you can start reading the signals. This tells you exactly when you need to jump in and figure something out. And, this is just as critical, when you need to leave the process alone.
So if all your data points are just kind of bouncing around randomly between those control limits, your process is what we call in control. And that's a good thing. It doesn't mean it's perfect, but it does mean it's stable and predictable. The variation you're seeing is just that normal background noise. And the number one rule here? Don't touch it. Seriously, if you try to fix this, you're probably going to make things worse.
But you absolutely have to act when you see signals of a special cause. These are non-random patterns, as you see on the slide, that are basically screaming at you that something fundamental has changed. This could be a single point flying outside the control limits, a long run of 7 or more points all on one side of the average, or maybe a clear upward or downward trend. Each one of these is a distinct alarm bell.
Let's look at the most obvious signal first, a point that lands outside the control limits. Because those limits are calculated to contain pretty much all of the normal variation, a point outside of them is a huge red flag. It's statistically super unlikely to be random chance. This is your fever spike. It's a loud, clear signal that something weird happened at that exact moment, and you got to find out what it was.
Now, here's a more subtle signal, but it's just as important. A run of 7 or more points all on one side of the average. See, while each individual point is still technically in control, the pattern isn't random at all. This tells you that the process average has actually shifted. Maybe a new batch of raw material came in, or a machine setting got tweaked, something changed.
You know, there's a great analogy for this. A control chart signal is like a baby crying. It doesn't tell you if the baby's hungry or tired or needs a new diaper. It just tells you, loud and clear, that you need to go investigate right now. The chart is the alarm, not the answer key.
All right, so let's say you've used your control charts, you've hunted down and eliminated those special causes, and now you have a stable, predictable process. You're done, right? Well, not quite, because now you have to ask the final, most critical question. Is our stable process actually any good?
Because being stable is not the same thing as being capable. I mean, you could have a process that is very, very predictably producing garbage. So now we have to ask, does our process meet the actual requirements that our customer needs?
And this brings us to what we call the two voices. First, you've got the specification limits. That's the voice of the customer. This is what they need, the target you have to hit, it's non-negotiable. Then you have the control limits, which, as we just learned, are the voice of the process, what your system is actually delivering. The whole game is about making these two voices line up.
And that, right there, is the definition of a capable process. It's when the natural variation of your process, that voice of the process, is narrow enough that it fits nice and comfortably inside the required specification limits, the voice of the customer.
We actually measure this with a pretty simple score. It's called the Process Capability Index, or CPK. Just think of it as a score that tells you how much safety margin you have between what your process is doing and what the customer requires. The bigger that safety margin, the higher your CPK score. And while it can vary, a really common target in a lot of industries is a CPK of 1.33 or higher.
So why does this one number matter so much? Just look at this chart. If your CPK is 1, you're still making about 2,700 defective parts for every million you produce. Not so great. But get to that target of 1.33, and it plummets all the way down to just 63. Push it even further to 1.67, and you're looking at less than 1 defect per million. The improvement is absolutely exponential. That's the incredible power of improving your process capability.
So that brings us to the final thought I want to leave you with. What special causes, what hidden fevers are lurking in the processes that you see every single day? And how could a simple chart, a control chart, help you spot them not after they've already caused a disaster, but long before they ever become a problem?
Hey, welcome to The Explainer. Today we're going to talk about a really powerful way to stop problems before they even have a chance to start. It's called Failure Mode and Effects Analysis, or FMEA for short. And trust me, it's a total game changer for building quality into pretty much anything, whether it's a new car or just a simple coffee maker. So let's start with a big question, one that probably keeps engineers and product managers up at night. How do you prevent a massive product recall? You know, how do you catch that one critical flaw before it gets out the door, before it costs you millions, and before it wrecks your reputation? Well, that is exactly the problem FMEA was built to solve. And look, this isn't just some academic theory. The stakes are incredibly high. A statement from the Ford FMEA handbook points out that a really disciplined FMEA program can prevent huge issues, like those massive vehicle recalls that we hear about. So this is a technique that was born in a high-stakes industry, and it delivers very real-world results. So here's what we're going to cover. First, we'll get into the right mindset, this idea of stopping failure before it starts. Then we'll define what FMEA actually is, look at a few different types, and walk through a really simple 3-step analysis. And most importantly, we'll talk about why this should matter to you and your team. Let's jump in. Okay, first things first. We have to get the mindset right. FMEA isn't about cleaning up a mess after it happens. It's about making sure the mess never happens in the first place. It's about baking quality and reliability right into the DNA of your project from day one. And this quote just says it all, doesn't it? FMEA is a before-the-event action, not an after-the-fact exercise. The whole point is to do this work early when making a change is easy and cheap. You're trying to anticipate failures, not just react to them. You're playing offense, not defense. So, with that proactive mindset locked in, let's get a little more formal. What exactly is failure mode and effects analysis? Now, I know that sounds a little textbooky, but what's really important here is that it's a system. It's a structured set of activities. First, you recognize how something could possibly fail. Those are the failure modes. Then, you evaluate the consequences, the effects of that failure. And finally, and this is the key part, you figure out how to prevent it from ever happening. So recognize, evaluate, prevent. That's it. And the payoff for doing this is huge. I mean, as the handbook points out, a good FMEA improves everything from the safety of your product to how happy your customers are. It helps you zero in on the biggest risks, It cuts down on those expensive last-minute changes, and it creates this amazing record of risk management that your whole team can learn from. Now, FMEA isn't a one-size-fits-all kind of tool. You actually use different versions depending on what you're looking at and when you're looking at it. So let's check out the 3 main types you're likely to run into. The source material really highlights 3 main types. There's a concept FMEA, which you'd use super early on. But the 2 you'll see most often are the design FMEA or DFMEA, which looks at the product design itself, and the process FMEA or PFMEA, which looks at how you actually build and assemble the thing. And this slide just illustrates the difference perfectly. A design FMEA is asking, how could this part break because of a flaw in the blueprint? A process FMEA is asking, how could we mess this up on the assembly line? One is all about the design, the other is all about the factory floor. And you absolutely need both to deliver a rock-solid product. Okay, so this all sounds good, but how do you actually do an FMEA? Well, the great thing is the handbook gives us a super clear and practical model that breaks the whole thing down into 3 really manageable steps. Here's the basic framework. Step 1, figure out what could go wrong and what the consequences would be. Step 2, dig into the root causes and figure out how often they might pop up. And step 3, look at what systems you already have in place to catch the problem. Let's walk through each one really quick. So step 1 is all about the failure itself. You brainstorm every possible way a part could break or a process could fail. Then, for each one, you ask the big question. How bad would this be for the customer? You know, a tiny scratch on a product is annoying, but a total brake failure is catastrophic. That judgment call gives you your score for severity. Next, you put on your detective hat. You've got to find the root cause. Why would that brake failure happen? Was it the wrong material? A flaw in the design? Once you figure out the potential causes, you estimate how likely they are to actually happen. Is this a 1 in a million shot or something that could happen pretty often? That gives you your score for occurrence. And finally, step 3 is all about your safety net. What tests or inspections do you have in place right now that could catch this brake failure before the car ever leaves the factory? Is it super easy to spot or almost impossible to find? How effective those checks are determines your detection score. So you've got 3 numbers: severity, occurrence, and detection. They're usually on a scale of 1 to 10. And this is where the magic happens. You multiply them together to get something called the risk priority number, or RPN. This score, which can be anywhere from 1 to 1,000, gives you this incredibly clear data-driven way to rank all your potential risks. It literally tells you which problems your team needs to attack first. So let's pull all of this together. Why does this whole structured process matter so much? Because it's about way more than just a number in a spreadsheet. I absolutely love this quote from the handbook because it really gets to the human side of things. An FMEA isn't some form an engineer fills out all alone. It's a catalyst. It's designed to spark conversation. It brings people from design, manufacturing, and quality all into the same room to share what they know and solve problems together. It builds a team that's focused on prevention. So what's the big takeaway here? FMEA is really a shift in thinking. It's about being proactive, not reactive. It gives your team a structured way to prioritize risks using data. And maybe best of all, it creates a living document of your team's collective wisdom, making sure you get smarter with every single project you do. And that brings us to our final thought. Just for a second, think about your own work, the projects you're on right now. What's that one potential failure, the one that kind of worries you, that a systematic, team-based analysis like FMEA could help you prevent? Thanks for watching.
You know that one problem, the one you think you fixed, but it just keeps coming back again and again? It's incredibly frustrating. Well, today, we're going to pull back the curtain on a super powerful method called 8D. It's designed to hunt down those recurring issues and get rid of them for good.
I love this old poem because it perfectly captures what we're talking about. A tiny, seemingly insignificant detail, just one nail, ends up causing this huge, catastrophic failure. A whole kingdom is lost. In our world, whether it's business or engineering, finding that nail is absolutely everything. And that is exactly what we're going to figure out how to do.
So let's talk about that recurring problem, right? Maybe for you, it's a customer complaint that pops up like clockwork every single quarter. Or maybe it's that one little defect on the manufacturing line that you solve, it vanishes, and then bam, a month later, it's back. It is maddening, it's expensive, and it just drains everyone's energy.
So why does this happen? Well, it's because we get caught in what's called the firefighting trap. We see smoke and we grab the extinguisher. We put out the fire, but we never stop to ask, hey, what started this fire in the first place? We're treating the symptom, the obvious thing that's right in our face, instead of finding the underlying disease. And, as long as that disease is there, the symptoms are always going to come back.
So how do we break out of this cycle? We do it with a really structured, systematic approach called Global 8D. Now, don't let the name fool you. This is not just some boring corporate procedure. Think of it more like a disciplined, team-based detective investigation. The whole goal is to get past the obvious stuff and find the absolute truth of why a problem is happening. The whole investigation follows these 8 specific steps, or disciplines. You start by getting the right team together and then describing the problem with surgical precision. Next, and this is key, you put a temporary fix in place to protect your customers while you do the real work, digging deep for that root cause. It's only after you've found and proven that root cause that you can develop a permanent solution, put it in place, and change your systems so this can never happen again. And of course, the final step is to celebrate the team's hard work. See? It's a really logical flow from just stopping the bleeding to curing the disease for good. And that brings us right to the heart of the whole 8D process. D4, defining and verifying the root cause. This is where the real detective work kicks in. We are not interested in the easy, surface-level answer. We're on a mission to find the fundamental, rock-bottom reason the problem happened. And what's our number one tool for this investigation? It's a technique that's so simple you might almost dismiss it. It's called the 5 why method. You state the problem, and then you just keep asking why over and over again, kind of like a toddler. Each answer you get becomes the basis for your next why. This process lets you peel back all those layers of symptoms, one by one, until you drill down to what's really driving the problem. But here's a pro tip. A truly deep investigation doesn't just stop at one line of questioning. A really solid analysis stands on 3 legs, like a stool. First, there's the specific leg, which asks, why did the actual technical thing fail? Then you have the detection leg, which asks, okay, why didn't our quality checks catch this before it got out? And finally, and this is the most important one, the systemic leg asks, why did our entire system let this happen in the first place? You have to answer all 3 to build a solution that's truly permanent.
All right, enough theory, let's make this real. We're going to walk through a case study. I want you to imagine we're an auto company, and we're just getting slammed with warranty claims for leaking windshields. Our customers are angry, the costs are racking up, the crime scene is set. Time to start the investigation.
So the team gets together, and their first finding is that the robot applying the sealant isn't putting on enough of it. Seems obvious, right? So the first impulse might be to say, okay, just program the robot to apply more. But that's just firefighting. A good detective team asks, but why isn't the robot applying enough? And by asking that simple question, they discovered something that was totally hidden. The sealant was actually drying out in the nozzle during long pauses in production.
Let's just walk through the 5 whys for this specific problem. Why did it leak? Because there was a gap. Okay, why was there a gap? Because the sealant bead was too low. Why was the bead low? The robot's nozzle was partially clogged. Why was it clogged? Because the sealant dried up inside the tip. And now for the final critical question, why does it dry? Because the robot was sitting idle for more than 20 minutes between cars. Boom, there it is. We went from a really vague symptom to a specific, measurable root cause, idle time.
But wait, we're not done yet. Remember that second leg? Detection. Why didn't we catch this problem before the car left the factory? Well, the investigation found that the manual inspection process they were using just wasn't fast or frequent enough to spot this kind of random failure. Our quality control system had a huge blind spot, and it was letting bad cars slip through to our customers.
And all of this leads us to the most critical discipline of all, D7, preventing recurrence. See, the goal isn't just to fix one robot on one assembly line. The real goal is to change the entire system so that this kind of failure can never, ever happen again. Not on any line, not for any product, ever.
So when the team asked why one last time, they finally hit the jackpot, the systemic root cause. Why was this idle time never controlled? Because it had never been identified as a critical thing to watch in their official equipment standards. And why not? Because there was no formal business process that required experts to identify and test all the critical variables when they launched a new product. The real failure wasn't the robot, it was a broken system. Just look at the difference in thinking here. It is profound. The temporary symptom-level fix is, just clean the nozzle more often. That's firefighting. That's a Band-Aid. The permanent, systemic solution is to update the company-wide equipment standards to make the nozzles automatically purge themselves after a set idle time. And even better, to create a new mandatory process that ensures this kind of variable is never ever missed again on any future products. See the difference? One fixes a leak, the other fixes the company.
So let's bring this all home. Let's tie it all together and go back to our story about the kingdom and the nail. Why does this deep, disciplined, almost obsessive approach matter so much?
It matters because cause and effect is a real, unbreakable chain of logic. And you can actually test your root cause analysis by working backwards, using what's called the therefore test. So if not enough nails were available, therefore the shoe was lost. If the shoe was lost, therefore the horse was lost. It's an unbreakable chain. A really solid root cause analysis creates an equally solid chain of logic that goes all the way from your solution right back to the customer's problem.
And honestly, the business case here is just a no-brainer. If you stop at the symptom level, you are guaranteeing that the problem will come back. That means endless scrap, rework, and just money down the drain. But a true root cause analysis that actually fixes the system, that leads to a permanent solution. That's money in the bank, and it means happy customers.
But listen, none of this, absolutely none of it, works without the right culture. There's a great story about when Alan Mulally took over a struggling Ford. Every single project was being reported as green, on track, even though the company was losing billions. When a manager finally got the courage to report a red project, Mulally stood up and started clapping. He understood a fundamental truth. You can't fix secrets. This whole process demands a culture where it's safe to bring problems out into the open so they can be solved.
And let's never forget the ultimate goal here. From the first temporary fix all the way to the final permanent solution, every single action you take in the 8D process has one singular objective: to be 100% effective at protecting the customer from ever experiencing that problem again. So I'm going to leave you with this question to chew on. What are the small overlooked details, the missing nails, in your own work, in your own processes? Finding them isn't about blaming anyone. It's about making everything we do better, stronger, and more reliable. Thanks for tuning in.